Right, so the last section of probability is going to be dealing with tree diagrams. And so a tree diagram is used when we want to show two or more events happening in succession. So there's going to be two different events occurring. And so a tree diagram will look something like this. Okay, so we have one event and there's one outcome, let's say A or B. And then after that, there's another event, let's say A or B again. Okay, and so this is what a tree diagram will look like. In these positions, you'll find the probabilities. So you're going to write some probabilities here. And remember that the sum of these two probabilities always have to be equal to 1 because probabilities have to add up to 1, right? And so they're going to ask you to find certain probabilities. And just things to note is if you're going across branches like here and here, we're going to multiply these probabilities together. So if I was to go here, here, you multiply this one and this one together like this. Okay? So if you're going across branches, we multiply. Now, if we're choosing different routes, so for example, I'm going to go this way first, and then I'm also going to go this way like this, okay? If you're choosing two different routes, then we're going to sum up each individual branch. So we're going to multiply these two here first, and then we're going to multiply these two as well, and then we're going to sum the values together to get one probability. So we're just going to practice some questions regarding this, so let's move on. Right, so we have Mr. Dixon plays golf. The probability that he scores par or under on the first hole is 0.7. Okay, so first things first, we need to draw our tree diagram. Okay, so the options are he can score par or under, and then if not, he's not a par, right? So not par, write it like this. Okay, right. So the probability of scoring par or under in the first hole is 0.7, meaning that this not par will be equal to 0.3, right? Because it has to add up to 1. Now, if he scores par under the first hole, the probability he scores par under the second hole is 0.8. So once again, from here now, this is the second hole, so this is par or not par again. Okay, so in this case, if he scored par, so in the beginning is 0.7, then he's going to score par again with a likelihood of 0.8. Therefore, this will be 0.2. Now, if he doesn't score par on the first hole, the probability that he scores par under is 0.4 in the second hole. So par or not par here as well. So if he doesn't score par, which is 0.3, the probability of scoring par in the second hole is 0.4. And therefore, this will be 0.6 because they all have to add up to 1. So this is our tree diagram here. Right, B, state whether the event scores par or under on the first hole and scores par or under in the second hole are independent. Remember, independent means that one event does not directly affect the probability of the second event happening, okay? But in this case, this is not independent. The reason being is because, as you can see, depending upon whether he scores par or not, the likelihood of scoring a par on the second hole is different, right? So these values are different. Now, if they were the same, it would be an independent event. However, because they are different, it means it's not independent, meaning the first hole score affects what he gets in the second hole. Right, C. Find the property that Mr. Dixon scores par under on only one hole. Okay, so he scores par under on one hole only. So in this case, let's find some routes of scoring par under in one hole only. So one way he can score par under would be to score par on the first hole and then not par on the second hole, right? So we're going across, so we're going to multiply 0.7 times 0.2. Now, another way he can score par or under in one hole only was to not score a par on the first hole, but then score a par on the second hole. So that's going to be 0.3 times 0.4. And now, because we've got two different routes, we're going to add them together like this. And so therefore, this value would give us equal to 0.26, like so. Let's try another question here. So a biased coin is tossed 3 times and it's recorded whether it falls heads or tails. The probability of heads is 1 over 3. So the first toss, we get either heads or tails, right? And the probability of heads is 1 over 3 because it's a biased coin, meaning that tails is 2 over 3 as well. Now, it doesn't give us any more information, so therefore we can say the second toss, once again, heads or tails, is going to be the same probability, meaning that actually in this case, the events are independent, unlike the previous example. Same thing for heads, tails, 1 over 3, 2 over 3 like this. Now he tosses it 3 times, we actually have to do one more branch like this, so heads, tails, heads, tails, heads, tails, and heads and tails. But the properties are still the same, so 1 over 3, 2 over 3, and so on. Okay, right, in part B, they're asking us, find the probability that the coin lands on heads all 3 times. So the root is going to be heads, 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 right? So for this one, remember I have to multiply, so 1 over 3 multiplied by 1 over 3, multiplied by 1 over 3 like this, which will give us 1 over 27. All right. In part C, find the probability that the coin lands on heads only once. So there's going to be multiple ways that he lands on heads once. Okay, so the first thing would be, if he lands heads on the first one, then the second 2 has to be tails, tails, right? So So this would be 1 over 3 times 2 over 3 times 2 over 3. That's one way of getting one head only. Plus, let's find a second root. So if you get tails on the first one, then you get heads on the second one, and then tails on the third one. So it'll be 2 over 3 times 1 over 3 times 2 over 3. And lastly, he can go for maybe tails on the first one, tails on the second one, and then heads on the last one. So we're going to be adding 2 over 3 times 2 over 3 times 1 over 3 like this. And we're going to 3 different roots, so there's 3 different sums we're going to add together. And so therefore, this will give us 4 over 9, like so. All right, D. So they're saying the whole experiment is repeated for a second trial. So basically, this is one trial, and now they're going to do a second one again, okay? And so they're saying find a property of obtaining either 3 heads or 3 tails in both trials. Right, so in part B, we found the property of 3 heads, right? And that was equal to 1 over 27. So now we need to find the property of 3 tails, okay? So that's just going to be tail, 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 which would be 2 over 3 cubed, like so, okay, which is 8 over 27. Now they're saying in the first trial, he's going to obtain 3 heads, and then 3 heads again in the second one, right? So therefore, the property will be 1 over 27 times by 1 over 27, like this. Or he can get 3 tails in the first event, and then 3 tails again in the second one. So 8 over 27 times by 8 over 27, and we're going to add them together. This will give us, therefore, 65 over 729. So as long as you clearly state the root you're taking, just to visualize it yourself, and then multiply, make sure you find every single root, and then go about multiplying and summing correctly, then all these questions should be relatively simple. Let's just try one more. So a bag contains 13 tokens, 4 blue, 3 red, and 6 yellow. 2 tokens are taken or drawn from the bag without replacement. Now this without replacement is important. Okay, so let's draw our tree diagram. So in this case, there's 3 different options, right? So there's actually blue, red, and yellow. The property of blue is 4 out of total, which is 13. Red would be 3 out of 13, and yellow would be 6 out of 13. Now that's token number 1. Now token number 2, once again, there's 3 options for each one. 1, 2, 3, and 1, 2, 3. Blue, red, yellow. Now for the first one, if a blue was taken, remember it's without replacement, right? So we've taken 1 out of the 4, meaning there's only 3 left. So there's going to be 3 over, and because we've already taken 1 out, rather than 13, the total number is actually going to be 12. So 3 over 12. Right. For red, no reds has been taken, so there's still 3 reds in total, and it's out of 12. And yellow as well, there's still 6 remaining out of 12. Now let's say we took 1 red out in the first token. The number of blues is still 4 out of 12. Because we took 1 red out already, it used to be 3, so now it's now 2 out of 12. And yellow, there's still 6 out of 12, like this. And finally, if I was to take 1 yellow out in the first one, number of tokens of blue is still 4 out of 12. Red is still 3 out of 12. And yellow now is going to be 5 out of 12 because we took 1 out of the 6. So once we've drawn a tree diagram, let's answer the question. So find the property that both tokens are yellow. So what's the root for yellow? Will be yellow like this and yellow like this. So it'll be 6 over 12 times by 5 over 12 like this, which will give us 5 over 26. Right, the second, part B. A third token is drawn from the bag. Write down the property that the third token is yellow, given that the first 2 are yellow, right? So that's going to be yellow, yellow, yellow. So we need to actually do another one. So it's going to be 6 over 12 times by 5 over 12. Now, if I took another yellow out, right, that'd be 4 out of 11, like this. So that's going to be probability of 3 yellows taken out. And this would give you 10 over 143. Find the property that all 3 tokens are different colors, okay? So it's going to be blue, red, yellow, right? So the property of, let's look at a root. So let's say blue, and let's go red, and then we need to draw one more section. So the first is blue, 4 over 13, times by red would be 3 over 12, times by the last token has to be yellow, right? And so there's still going to be 6 yellows, and there's going to be 11 tokens left. Now there's actually going to be 3 different routes to this. We can choose red, blue, yellow, or we can do like red, yellow, blue, and so on and so on and so on. It's all depending upon the number of scenarios. So it's actually going to be multiplied by 6 in this case, with 6 different combinations or ways of getting 3 different tokens. And so this is going to be the property that all 3 tokens are different colors. So as I said, you have to clearly state what route you're going to take to achieve the outcome, and then just go about finding each property respectively.